Okay, so we so far for the first 6 weeks, we have covered the first 5 chapters from the set and logics to the introduction to the number theory in chapter 5. Okay, and we will have our midterm examination on next Friday. So today we will review the first 5 chapters that we have covered, and we will share some of your report for helping others to get prepared for the midterm examination. In chapter 1, set and logics, we have had a whole big pictures of the discrete mathematics from chapter 1 to chapter 9 and others, and we shared the structure of the textbook and the chapters that will be covered in this course, and I gave you all the exams with the solutions, so you can study without difficulties. 내가 이걸 준 이유가 뭔가 하면 여러분들이 대학교 들어오기 전까지 공부를 엄청 많이 하면서도 대개 그 자습서라든지 문제집들을 풀면서 공부해온 습관이 있어서 대학에 들어와서 답이 없는 문제들을 계속 접하면은 막힌 다음에 해결하는 능력들이 굉장히 떨어져서, 그래서 그 얻으셨다는 과정으로 문제를 따로 주고 답을 따로 줘서 그 문제를 풀어보고 답을 맞춰볼 수 있는 그런 기회를 준 거예요. 근데 보통의 수학의 이제 어드밴스드 코스로 가면 보통 답이 없이 문제를 풀어서 그걸 발표하고 이제 그러면서 틀린 걸 지적받아가면서 고치는 훈련을 해요. 원래 수학 자체가 없는 지식을 새로 만들어가는 것이기 때문에 알려진 문제를 푸는 그런 학문이 아니기 때문에. 자, 그런데 어쨌든 early 스테이지에서는 이게 도움이 될 것 같아서 여러분들한테 도움이 줬고, 또 디스크리트 매스는 이게 뭐 우리 학교에서만 배우고 여러분만 배우는 게 아니라 온 세상의 뭐 거의 모든 대학에서 그 모든 대학생들이 거의 비슷한 콘텐츠를 배우는 내용이기 때문에 글로벌 스탠다드에 맞춰서 거의 비슷하게 그 세계의 그 명문 대학들이 배우는 그런 같은 레벨을 여러분들에게 제공해 주려고 만들었어요. So you have studied and you have solved and you have discussed this problem so far. It was reported as your PBL report, and I introduced some notations, and also I gave you a big picture of mathematics and where discrete math content is located in the college mathematics. In chapter 1, first 2 chapters are basically review of the mathematics that most of you have studied during the secondary school years. And we added some new concept and notations. And in chapter 1, and you already knows well on sets and propositions and conditional proposition and logical equivalences. And in addition to that, we introduced the quantifiers such as for and such that and there exist. And also we covered the nested quantifiers in order to proceed the chapter 2. And in here I have made the code for you to check what you have studied in the Python-based Sage languages, and this can be used to deal with the large size data. And you can find the union and intersections. You can compare the two sets, and you can find the solution of equations, and in set. And this command gives you whether the given set is a subset of the other one or not. And this command gives you the list of all the subsets of a given set, which is an element of the power set of a given set. If you add some others, where if you have some other sets like this, this also gives you the whole, the list of the power sets like this. Since you have 1, 2, 3, 4, 5 elements in a given set A, so you have the 2 to the 5th power of the element in the power set of the given set A's. And the unions and intersections and differences can be also treated with the code, and differences can be found, and Venn diagram was introduced, and cardinality can be counted easily. This may looks very simple, but when you have a large element of Z, then you can, this code can be very useful. Anyway, we covered the proposition, 명제. Proposition is a sentence, either true or false. And the conjunctions and the truth tables was introduced, and that gives you the truth table and negations, etc. So you have, and also the quantifiers. Quantifiers were introduced. And this is the way of writing. And also this was used when you do make a proofs of the given propositions. And those are the commands that you can use, whether this given number is real or not. And etc. And that's the laboratory that you have studied. And generalized Morgan's law for logic. This was also a useful tool when you use quantifiers. And the example shows how you make a argument is proved. And next, the quantifiers is a consequence of the earlier section of quantifiers. And the definitions and proofs. And with those quantifiers, you can really prove the notations that you have used without recognizing the deep meaning of the mathematics of given equations. 여러분들이 이제 이런 것들을 고등학교 때 많이 써서 계속 써왔었잖아요. 근데 이게 사실인지 아닌지는 이런 식으로 증명을 하는 거예요. 이게 어떤 의미가 있냐면, 이필런과 델타는 어떤 의미가 있는 거냐면, 생물학에서 현미경이 없을 때는 사람이 뭐 이렇게 도대체 병이 왜 생기는지, 어떻게 하면 병을 낫게 하는지 그 원인을 사실은 모른 채로 대충 보고 했던 거, 처리했던 거 아니야? 근데 현미경이 나오면서 이제 그 상황에 대해서 그 데이터를, 그 자료를 가지고 보면서 그 다른 상황들을 보고 이게 있으면 이런 상황이 생기고 이런 그 생물체가 그 안에 있으면 저런 상황이 생긴다. 그래서 그걸 제거하고 하면서 답을 찾아가면서 인류를 향상시켰잖아요. 이 입실론 델타가 어떤 의미가 있냐면 수학에서의 그 현미경 같은 역할을 하는 그런 거예요. 이렇게 무한소 이런 경우에 그게 도대체 그 안에서 무슨 일이 이루어지는지 그냥 이 그래프 도표에서는 눈에 보이지 않지만 입실론 델타를 사용하면서 더 확대하고 또 확대하고 무한한 단계까지 확대해 가면서 진짜 그 무한소 개념에서의 벌어지는 상황을 엄밀하게 증명을 하면서 수학이 획기적인 그런 발전을 하게 된 거예요. 생물학 라이프 사이언스에서 현미경의 발견이 그 학문적인 혁명을 이루었듯이 수학에서는 이 무한소를 볼 수 있는 이런 그 입실론 델타와 같은 그런 도구가 바로 그런 역할을 해줘서 엄밀한 수학이 만들어졌고, 그 엄밀한 수학이 있었기 때문에 일단 사이언스나 엔지니어링이 발전할 수 있었던 거예요. 이런 게 있었기 때문에 인공위성을 또는 미사일을 쏘아 올려도 그게 1000km, 5000km를 가서 저기 달나라까지 가고 해도 정확하게 우리가 기대했던 일이 벌어질 것이라는 확신을 주게 하는 근거를 준 게 바로 이런 엄밀성 of mathematics. Anyway, and in chapter 2, proofs. In chapter 2, we have learned the several types of technique for the proof, the method of proofs. And also, we learned the mathematical inductions, and also strong form of math inductions and well-ordering properties. And in here also we made some code that can be used for you to find there are different type of the proofs, such as the proof by cases, checking all the cases to prove the given proposition, and exhaustive proofs. And the proof of equivalence, we show one thing by proving the other equivalent propositions. In that case, the quantifiers that we have studied and truth tables are the ones that can be effectively used when we do the proof of equivalence. And existence proof. This is the show. This is the tool. One important tool to show whether a given statement is true or not, by finding the existence of an element that satisfies a certain properties. Next, proof by contradictions, and that's another important tool. This is the part. This is also the proof by the equivalence relations, showing this is same as showing the contrapositive. And also, the proof by contradiction is also a better tool to show a given sentence whether it is true or not, because this proof by contradiction offers us more opportunities and conditions and tools to be used to prove the given proposition. And mass induction, yeah, you have studied it, and this is also a very important part of the chapter 2. And these kind of tools can be used very effectively. So when you show a given sentence is true or not, and you can easily check the cases for each ends. Not all, but if you check the given sentence for enough number of the cases, if everything's are all true, then you can think that sentence is always true. So you can attack it with a positive attitude. And so also, which can be considered as a conjecture. So everybody can try to prove it. But if you find one example which is not true, then you can easily think we don't have to prove because that's not true in general. Okay, so these days this type of approach at the early stage of proof is also very important. Everybody should know that. Okay, like this. Tilings and tiling problems. And strong form of induction. What's the difference between the mass induction and strong form of mass induction? Mr. Yang Seung-chan, what's the difference between mass induction and strong form of mass induction? Basis step is same. We show n is equal to 1 first, done. But the second step, induction step, is a little different. In mass induction, we assume that sentence is true for n minus 1. Only assume that. Then you show that the sentence is true for n. That's enough. But for strong induction, your induction assumption is it is true for all k which is less than n. You not assume only one case, but also you assume that it's all true for whole numbers k except n, and then use whole those property to show it is true for n. Okay, so strong induction has more assumptions, but basically those two are same, because if the mass induction works, if one thing can be proved by mass induction, that means if n is true, so 2 is true. The case it is true for the case n is equal to 2. Then 1, 2 is true. Okay, so with the mass induction, we know that statement is true for 1, 2, 3. Since the statement is true for the first 3 cases, so it is also true for the n is equal to 4 by mass induction, if it is proved by mass induction. So if a statement is proved by mass induction, then it definitely the strong form of mass induction should work too. So basically they are equivalent. Okay. Anyway, but strong form of mass induction has more induction assumptions. So you have the larger number of the conditions to be used. So it can make it a little bit easier. Then well-ordering property is the one that if you have a set of positive numbers, positive integers, that it always has the smallest element in it. That also, they are all actually equivalent statements. We have learned that. And we introduced the floor function and ceiling functions, which is used over and over again, etc. Okay. Next, chapter 3. Chapter 3. functions and sequence and relations. Okay. What we have studied in here. Anyway, yeah, in chapter 2, yeah, we reviewed the concept of functions and we defined the strings. And actually, the research center at Tsinghua University that I visited yesterday was field medalist Yao's names after, and Yao Mathematical Science Center is leading the string theory, which is mathematics and also the big subject of theoretical physics, string theory. Anyway, relations and equivalence relations and matrix of relations. So from the relations we found a corresponding matrix representation of relations, and that's what we have studied in here. And here we defined the domains and codomains and range and definition of one-to-one and on-to, and yeah, modular arithmetics was covered, and the floor functions and ceiling functions was introduced, and it was examined for the given examples in the textbook, and we saw some story problems related with it, and one-to-one functions and on-to functions and bijective functions, and those are the things that you have studied. Surjective functions and bijections. Inverse function was introduced, and yeah, operators was also introduced. And sequences and strings, finite sequence, and increasing, non-increasing was introduced, and yeah, summation notations. And string was defined as a finite sequence of characters, like this. These are the examples of strings. They are not commutative. And substring was defined, and the relation was treated, and binary relation was introduced, and yeah, corresponding directed graph was introduced. From the graph, yeah, from the relations we can think about graph. From this graph we can think about the corresponding matrix as well, and those are the things that we have studied. And inverse and equivalence relations. What's the definition of equivalence relations? Okay. The equivalence relations that satisfies the three properties. A relation that satisfies the reflexive and symmetric and transitive, we call it is an equivalence relations. If you have equivalence relations, then a set can be partitioned. We can have a partition of a given set with that equivalence relations. Okay. And yeah, this shows you the digraphs from the relations. 그러니까 이 코드가 여러분들 이게 비주얼라이제이션도 시켜주잖아. 굉장히 많은 것도 한눈에 딱 볼 수 있지. 굉장히 복잡한 시츄에이션도 릴레이션도 그림으로 보면 서로 어떤 대칭성이 있는지, 또는 어떻게 몇 개로 나누어지는지, 아이솔레이트 된 게 있는지, 뭐 루프가 있는지, 그런 것들을 그림을 그려서 볼 수 있죠. 그러니까 이런 툴, these are those kind of tools will be good for you to have. Anyway, equivalence relations and partitions, and if you have partitions, then the counting techniques will be also used to analyze it. A matrix of relations. From the relation, we can define a matrix like this. And from the relation, you can find the corresponding matrix representation of the relations like this. And I think that's the chapter 3. And next, chapter 4, algorithms. I think this was really the important part of the early part of our discrete mathematics. And in here, we really went through in details with the pseudo algorithm, pseudo code of the given algorithm. And so I gave you the whole code for sort the data and give them in orders and making a list of it and finding the location of the given number in the orders. So we introduced the examples of algorithms, including a linear search algorithm and binary search algorithms. binary search algoritm이 어떤 거였어요? And sortings. 그러니까 이제 순서대로 배열하는 방법이죠. 그렇죠? 그 미련한 방법으로는 처음부터 하나씩 비교해서 계속 작은 게 아래로 내려가고 그러면 큰 게 위로 밀려나게 되겠죠. 그런 식으로 쭉 하면은 그러면 배열이 될 거고, 그리고 또 하나가 중간에 집어넣은 것이 제자리를 찾아 넣게 하려면 크고 작은 거 비교해서 자꾸 그 빈자리를 만들어서 채워 들어가면 될 거고. So I made the code for those so you can really sort or insert. And in this chapter we have learned the how to analyze the given algorithms, and these are the tools. And the analysis of algorithms here. So in here we introduced the big O notation and the omega notation and theta notations. What are the concept of this notation? Yeah, big O notation, that's the one that you should know, and you will see in the midterm examinations in polynomials. And this shows how those analysis can be analyzed. And you may see how to show a given function can be represented with big O notation or theta or omega notations. Okay, and those are the analysis of algorithms. Okay, and recursive algorithms is also important part, and Fibonacci sequence and this robot working the sequence was introduced, and it was coded, so you can really compute. So for Fibonacci occasion, if you want to find the 123rd term of Fibonacci sequence, then this is the term that we are looking for. And then we introduce some equations with those sequence. In this case, it was the equation with the Fibonacci sequence. The last, chapter 5, it was an introduction to number theory. In here, we introduced the divisors and representation of integrals and integer algorithms, and we also introduced the Euclidean algorithms. Okay, here. Okay, divisors. What's the Euclidean algorithm can do? Okay. So in chapter 5, we started from divisors and quotient and the representation of integers, including the fundamental theorem of arithmetics. And then we did study the Euclidean algorithm that handles the GCD and LCM of the given integers. And this is how to find the integers, divisors, and prime definition of definition of prime number and definition of composite, which is not prime. And this is the way to check whether the given number integer is a composite or not. This is a very simple condition, but it reduces a lot of work to when we check whether a given integer is composite or prime. And testing whether the given number is prime. And this algorithm gives us whether a given number is prime number or composite. And the fundamental theorem of arithmetic says that a given integer can be written as a product of prime numbers. And we showed there are infinitely many prime numbers. And we defined GCD and LCM, and we found the relationship between the given two numbers and GCD and LCMs. Finding the LCM, and like this LCM can be found in this way, and also the product of GCD and LCM of two numbers are exactly same as the product of two numbers because of this proof. I think that's it. And also, we introduce the binary number system and octal number system and decimal number system and hexadecimal number system, etc. And also, this can be easily done with the code, the binary explanation, presentation, and also changing a given number. If you change it as a 6, you can 8 like this. You can what? Switch the basis representation with the same code that I introduced for you. So it works for all the rest of the code and hexadecimal to hexadecimal. And addition of binary numbers, etc. Hexadecimal additions. I think that's what we have learned. And this section 5.3, Euclidean algorithm, was the last section that we studied. And here, here, the Chinese remainder theorem can be improved and generalized when we analyzed the GCD of the given numbers. The interesting fact is from the Chinese remainder theorem here, the Euclidean algorithm tells us GCD of A and B is same as GCD of B and R. This A is a big number, but this R is a much smaller number. So when you find the GCD, instead of finding the GCD of these two big numbers, you can do the same thing with the much smaller number R compared to the big number A. And you can do it over and over again. So finding GCD of AB can be done with the much smaller numbers with this remainder from the Chinese remainder theorems. So we use it, then we can find really a very easy that you can find the GCD easily. And this is the algorithm. And anyway, if you had 2 here and 2 here, then you will have common the GCD of these two numbers like this. And Bezos theorem also was introduced. And modular, inverse modular number was the last part of chapter 5. And as you see in the section 5.4, the knowledge of number theory was used, widely used in the study of cryptography, like what you see in here. I think that's the end of the first 5 chapters. Any questions before the final, before your presentation of your report?